Hello everyone, welcome to the Hands-Only Camcar Team Project Review. To start us off, I would like to introduce the team members. Cruz, Andrew, and Dylan, who are electrical engineers. Zane and Harrison, who are computer engineers.
Unmanned surface vehicles are used in law enforcement, search and rescue, and space exploration, giving operators visual capabilities in hazardous environments. Typical control methods for RC vehicles involve a video game console controller. But what if an operator's hands are restricted or otherwise unable to use a controller? This question led us to develop a hand gesture control method. Our goal for the project was to develop and build a wireless, battery-powered RC car equipped with a positionable camera capable of live feed video and controlled by a series of hand gestures at a cost of under $375. Important factors were portability, speed, and responsiveness. A critical factor that we identified was the responsiveness, with a goal of a low control delay and low live video feed latency.
Our car control subsystem consists of parts contained on mostly the bottom of the car as well as the right-hand glove. Starting with the car, it consists of a motor driver connected to the left and right wheel motors. The motor driver is powered by AA batteries held on the top of the car. The motor driver is connected to an Arduino Uno, which is connected to the Bluetooth transceiver to receive commands, and the Arduino Uno is powered by a 9-volt battery. On the glove side, the glove has an Arduino Nano, Bluetooth transceiver, a power source which is also a 9-volt battery, a flex sensor, as well as an IMU. This acts as the controller to tell the car. From our flowchart here, you can see how each command can be then translated into movements by the car. Each of them are based off of wrist tilted movements and will wait about a quarter of a second in between, which allows for better usability. The camera control subsystem consists of that of the left-hand glove as well as the servo motor subsystem on the car. The servo motor subsystem is the servo motor connected to the Arduino Nano, which is connected to a Bluetooth transceiver connecting to the glove, as well as a power source powering the Arduino Nano, which is a 9-volt battery. The glove is the exact same as the right-hand glove, just made on the left hand. This flowchart is much simpler than the one discussed for the car control, as you only need to figure out whether the wrist is tilting left or right. Another added feature is that when the glove is closed, opened, and then closed within 1 second, the servo motor will then reset to 90 degrees or straight looking for easier usability.
Once the Raspberry Pi is powered, the live feed program will start up automatically as a service. This program creates a 30 frames per second 144p resolution live stream and hosts it on a user interface that is accessible from any client device on the same network as the Raspberry Pi. Due to the Raspberry Pi being an older model, it can only connect to 2.4 gigahertz Wi-Fi. Once the Raspberry Pi is powered, the live feed program will start up automatically as a service. This program creates a 30 frames per second 144p resolution live stream and hosts it on a user interface that is accessible from any client device on the same network as the Raspberry Pi. Due to the Raspberry Pi being an older model, it can only connect to 2.4 gigahertz Wi-Fi. Any user can access the interface by typing the Raspberry Pi IP address with the port 5000 in the URL. To go into the specifics of how the Python program works, it creates a web server for the live stream interface and continually asks for frames from the Raspberry Pi camera. We used a web framework named Flask to create our web server and expose it to the rest of the network. We use OpenCV to lower the resolution of each retrieved frame to 144p resolution to increase performance of the live stream and encode the frame to a JPEG image so that it may be used as a source for an image element on the web page. To further increase performance of the live stream, we limited the number of frames sent to the user interface to 30 frames per second.
The hardware used on our car includes one Arduino Uno, one Bluetooth transceiver operating in slave mode, two small DC motors, one L298N dual-channel DC motor driver, a single 9-volt battery powering the Arduino Uno, and a battery bank of 6 AA batteries powering the DC motor. For the car control, one Arduino Nano, one Bluetooth transceiver operating in master mode, a single accelerometer gyroscope sensor, a single 2.2-inch flex sensor, and a 9-volt battery powering the Arduino Nano were used. The camera module includes one Raspberry Pi 3 Model B, one Raspberry Pi camera module, a single DSM-44 servo motor, one Arduino Nano, one Bluetooth transceiver operating in slave mode, a single 9-volt battery powering the Arduino Nano, and a single 5-volt 2.1 amp battery pack, which powered the Raspberry Pi. Camera control includes one Arduino Nano, one Bluetooth transceiver operating in master mode, a single accelerometer gyroscope sensor, one 2.2-inch flex sensor, and a single 9-volt battery powering the Arduino Nano.
By the end of the year, we were able to hit all our quantifiable benchmarks. For our car subsystem, the car is only movable when the right-hand glove is fully closed in a 90-degree angle. The instruction delay is about 1/5 of a second. When the right-hand glove is tilted forward, the car moves about 1.5 feet per second. Likewise, when the glove is tilted backwards, the car moves at 1.5 feet per second. For forward left and forward right, when the glove is tilted in those directions, it moves at about 1 foot per second. And when the right-hand glove is tilted right and left, the car will turn right and left at half pi over 2 radians per second and pi radians per second, respectively. Similar to the car subsystem, our mounted camera is only movable when the left-hand glove is in a fully closed fist at 90 degrees angle. The camera command delay is about 3/4 of a second. And for the camera to rotate or travel 180 degrees, it takes about 4 seconds. And in general, our camera turn speed is about pi over 4 radians per second. Lastly, our stream latency for our live stream video is 1/4 of a second.
One of the biggest strengths of our project is the response time of both the camera and the car. With both being around 250 milliseconds, the delay between hand movement and car and camera movement is almost instant. Another strong point is the live video feed. While at the start, we had some problems with a laggy video that would freeze at times, it is now lag-free, real-time, and has a clear quality, so nothing is blurry on screen. Another strong point was the simplicity of use. For our second demo, we had somebody not in our group use the glove to drive the car, and he was able to drive it through the obstacle course without any trouble. The speed at which the car moved was also a big plus. While on carpet, it appears somewhat sluggish at times due to some of the weaknesses I will mention soon. but on hardwood, it is quite fast, almost twice as fast as we initially planned for. With rubber wheels, this would have been the optimal way to use it, which leads me to the weaknesses. One of the biggest weaknesses our project has is the material of the wheels. The wheels being plastic inhibited the car's ability to reliably get out of dark, deep carpet because it would lose traction. Another weakness is the number of batteries that must be used to power the car. Many batteries are used during testing because 4 and 9-volt batteries are needed at a time to run the car and camera with the gloves, and 6 AA's are needed to run the car with the motor driver. Having a better way to power the car from one central source would help with this problem. The chassis purchase came with its own set of problems as well. With the built-in motor for the wheels, it left little room for us to put components on, so it was decided not to use the 2 back wheels, which led to another set of problems, because we had to use a roller ball bearing instead. And with the full weight of all the components toward the end of the project, it would sometimes drag through the carpet instead of roll. This would sometimes throw off our forward left and forward right motions because it would get caught in the tiny tracks that it left previously and it would knock itself off course.